So first of all, the asymptotic giant branch, or AGB phase, is one of the final evolutionary phases of the lives in the stars, with an initial mass between 0.8 to 8 solar masses. So as these stars run out of hydrogen in their core, they will finally ascend the AGB on the Hertzsprung-Russell diagram, and they're here at the top right, so they're very bright, very cold, very red stars. The AGB phase is characterized by mass loss. These stars lose their outer layers by means of a two-step outflow launching mechanism. So first of all, the AGB star itself is pulsating, and with each pulsation, material is lifted away from the star to a region where the density is still high enough, but the temperature low enough for dust to condense from the gas phase. And this dust is then opaque to the infrared radiation of your star, and it absorbs the photon's momentum, accelerates away from the star. And as the dust moves away from the star, it bumps into the gas, drags it along, and launches an outflow. So pulsations facilitate dust formation, which then launch a dust-driven wind. Now, these stars lose their outer layers at quite a considerable rate, between 10 to the minus 8 to 10 to the minus 4 solar masses per year. In fact, these mass loss rates are so large that it's the process of mass loss that determines the subsequent evolution of these stars rather than the nucleosynthesis in their cores. And thanks to their outflows, these AGB stars are very important to the chemical enrichment of the ISM. About 80% of all gas comes from AGB stars and 35% of the total dust. But if you look at just newly formed stellar dust, they are thought to contribute about 70%. So they're very important to the ISM and everything that happens after. So if you think about a journey from a dark cloud to a protostar and a protoplanetary disk to finally a star and planetary system, and especially when you think of all the chemistry that happens along the way, you shouldn't forget about our friends, the AGB stars, which provide all the building blocks for this all to happen. And these are two quite famous examples of AGB stars. So here you have IRC 10216, also known as CW Leo. This is an image taken in the optical by Hubble. So here you see these dusty shells moving away from the star into the ISM. And this one over here is Myra. It's an image taken in the UV. Myra itself is somewhere over here blowing a bubble with its outflow, but also moving through the ISM and leaving behind this tail of material polluting the interstellar medium. And the tail is about 13 light years long in total. So let's dive into these AGB outflows a bit more, and this is a schematic overview of the star and its outflow. Now, the chemistry of the outflow is determined by the elemental carbon to oxygen ratio of the star itself, and this is all because of the strong binding energy of the carbon monoxide molecule. So all stars start out as oxygen rich, so you have a C/O ratio smaller than 1. You can then assume that most of your carbon will be locked up into CO because it really wants to form CO, leaving behind only oxygen, so you will have an oxygen-rich gas phase chemistry, and the types of dust grains that you form are silicates and metal oxides. If you then become carbon-rich, so your C/O ratio increases as you evolve along the AGB, for some stars, not for the Sun, for example, you will get a C/O ratio larger than 1, so more carbon and oxygen. The type of chemistry we'll then have is carbon-rich, and the type of dust grains that you form is like amorphous carbon, basically soot particles, and some silicon carbide dust grains as well. So the outflow can be divided into 3 main regions, and each are characterized by specific chemical and dynamical processes that are closely linked. In the inner wind, the chemistry is taken out of equilibrium because of these shocks caused by the stellar pulsations. And then if you move a bit outwards, we go, dust is able to condense from the gas phase, so this is the region where outflow is launched. So it's the micro-scale chemical process of dust formation that launches your macro-scale dynamical outflow. And then finally, in the outer wind, the chemistry has reached its terminal velocity, some 5 to 20 kilometers, 30 kilometers per second. And the chemistry in this region is very rich photochemistry, since the density is much lower, which means that interstellar UV photons can more easily penetrate this region and create a very reactive soup of atoms, ions, and molecules. So I'd like to point out just the scale of these things. So we go from the stellar surface, which is about 1 AU, to about 20,000 stellar radii, or 20,000 AU. So these outflows are enormous. And because of with the fact that they're an outflow, you also have these large gradients in density and temperature. You go from some 10 to the 13 particles per cubic centimeter at a few thousand Kelvin in the inner wind to less than 10 particles per cubic centimeter at 10 Kelvin in the outer wind. And it's precisely because you have these large gradients that you can have such a rich chemistry all within one object. In a dark cloud or a protoplanetary disk, for example, you don't have such a varied chemistry. All right. When it comes to chemical modeling, chemical models of these outflows, you can divide you can distinguish 2 to 3 categories. So you've got chemical models that are specific to the non-equilibrium chemistry in the inner wind. They take these shocks into account in a hydrodynamical way or maybe a semi-analytic way. Then you've got chemical kinetics models that are geared towards the photochemistry of the outer wind. And over the past few years, I've extended such a gas phase chemical kinetics model into the dust interaction zone by including dust-gas interactions as well. So dust and gas can bump into each other and form icy mantles, for example. Now, the story that I've been showing you so far is very nicely spherically symmetric and one-dimensional, but of course, nothing is quite as easy as it seems, and most AGB stars are not spherically symmetric at all. You've got large-scale asymmetry, such as this spiral around R Sculptoris. This is an image taken by ALMA. You've got CO emission here, as well as the dusty disk around L2 Puppis. So here you have a sphere image. So this dark band is a dusty disk. It blocks all the light. And you've got the 2 cones of light being scattered off the dusty disk. And I'll talk a bit more about this guy a bit later on. You also have, I'm part of the, together with Thaisa and Daniel, we're part of the ALMA Large Programme ATOMIUM, and this is our postcard. So you have 12 oxygen-rich AGB outflows here, all CO emission, red is going away from you, blue towards you. And none of them are spherically symmetric. And this was a bit by accident. The sample wasn't chosen for asymmetries or suspected asymmetries, but none of them are spherically symmetric. Some a bit more so than others. Like these ones are a bit fine. But here you've got a bipolar outflow, you've got some sort of a space rose, and this one has both a disk and a spiral, so it's really quite a mess. And this links the AGB phase to the next phase in its evolution, namely the planetary nebula phase. Let's go back. Planetary nebula phase, where it's long been known that you've got these beautiful, crazy shapes like the red rectangle, for example, and it might be, we think now that these shapes are already being produced in the AGB phase by means of interaction with a companion, so either a stellar companion or a massive planetary companion that's able to shape the outflow into these crazy structures that you can then later on see in the planetary nebula phase. All right. You also have small-scale asymmetry, so very close to the star. Here you have another sphere image of our door, so the dashed line is the stellar disk. This row was taken in December 2014, and then 2 months later, in January 2015, you see that not only is it quite blobby and not spherically symmetric, it also changes over time. So that's wonderful. Also small-scale asymmetries. And then recently, close to IRC 10^16, so the guy that I showed you before, you also have a very clumpy emission in different molecules close to the star as well as in the dust. And these asymmetries are likely caused by the convective motion of your star itself. It's a huge pot of boiling water, and this is a simulation of such an AGB star by Freitag and Höfner. So they have a wonderful star-in-a-box model, and you can see all these huge convective blobs moving up and down and creating a lot of havoc. Right. So for the rest of my talk, I'll focus on 2 main things, so mainly dust formation and then observed chemical complexities. So let's start with dust formation, because even though dust plays such an important role, it drives the outflow, we still don't really know how you go from atoms to molecules to some larger clusters to finally dust. And I'd like to stress again that it's a small-scale chemical process of dust formation that drives your outflow. So we don't know what the seed particles are. They sort of cluster together to form the dust, and this also implies that we don't know what the exact composition of the grain size distribution of the dust that goes into the ISM and continues on in star-forming regions. So there's 2 ways you can go about studying dust formation. In the carbon-rich case, you can go to to the lab. The NanoCosmos team has built a stardust machine that mimics a carbon-rich outflow as well as the processing of the dust in the ISM. So this tube, this very expensive tube, is able to sort of, well, yeah, just got a little AGB outflow right in there. So that's very impressive, and these are some of their results. So by including more C2H2, which is very commonly, well, has a very high abundance in a carbon-rich AGB outflow, you see that you can that this, including a more realistic amount of C2H2, you have a different size distribution and also a different shape of your, well, more grains, different grain size distribution, and also they're more porous rather than if you don't include C2H2. So these are just a few of the results, and that's all pretty cool that you can do it, but it's also very expensive. And for an oxygen-rich outflow, we don't have such a machine, and we have to go to a combination of observations and theory. So for oxygen-rich outflows, the situation is also a bit more dire. For carbon-rich, you know that it's basically soot formation. It's like a huge combustion engine. It's still not fully known how you make the dust, but still you've got a good clue. But for oxygen-rich outflows, we don't even know what the seed particles of the dust are. And aluminium oxides appear to be good candidates. And then Jels Boulanger created a hydrodynamical chemical model of the inner wind, and he found that he could make large aluminium oxide clusters, but only if the monomer was already present. So if he started out from just aluminium and oxygen, he couldn't make these large clusters. But we do know that dust is present close to the star. So here again, we've got the sphere images of Ardor, and these are all polarized light observations, so they show you that dust is present very close to the star, but the model can't make it. So maybe some cluster formation pathways are missing, maybe the reaction rates are incorrect or, well, missing as well. So for that, you have to go to your friendly theoretical chemist that can calculate all the ways that aluminium oxides can cluster together and form stable configurations. And then you can plug that into your new chemical model and see whether it works. Now, aluminium oxide is just one of the many, many molecules that could cluster together. You also have things like calcium titanate and other ones as well. But you do really need a collaboration between observations, theoretical modelers, and then also your chemist, either in the lab or with a computer. Because, well, one person can't do everything themselves. Right. So even though we don't know how the dust is formed, we do know that the dust is there, and that's what I've been including, dust-gas interactions within the chemical model. And these are, oh, I thought I removed that slide, so, but anyway, these are some observational evidences of why we know that dust-gas interactions do occur. So for example, SiO and SiS decrease within, are shown, observed to like decrease in a high density oxygen-rich outflows, and you also have these correlations of you've got SiC2, SiO, CS, SiS molecules that we think might go into dust, so their abundances decrease with increasing outflow density, so probably they are sequestered into the dust. But then the smoking gun is of course the observation of water ice around OHIR stars. So I included dust-gas interactions in the chemical model, and here I show you some results for an oxygen-rich outflow. The dashed lines are the results when you just gas-phase chemistry only. So you've got your parent species, they exist, and then they get photodissociated, so you've got a nice molecular envelope. If you include the dust-gas chemistry, and I have to admit, it's a dense outflow, the dust is quite cold, I tweaked it a little bit to make it more apparent, but this is not super unrealistic. You see that, for example, the water abundance decreases by 4 orders of magnitude, SiS here in purple by 2, SiO as well, and this is on par with what has been observed. And other species don't care about the dust, like CO and SO. Their binding energies are way too low, they don't want to stick onto the dust. Water, on the other hand, really likes to stick onto the dust, as you can see. Then we also thought a bit ahead of the composition of interstellar dust, which is thought to have the structure of a silicate core surrounded by an inner organic mantle, composed of refractory organic material, and then surrounded by an outer ice mantle. And this organic material is thought to be formed by photoprocessing of ices in the diffuse ISM. But if we already have ices in the AGB outflow, which we do have because things accrete from the gas phase onto the dust, perhaps this refractory organic material can already be formed within the outflow, which means that your dust would enter the ISM a little bit sticky, sort of having the refractory organic material being formed in the prenatal phase of your interstellar dust. So we included the photoprocessing of complex ices in our chemical model, and these are some of our results for a sample of carbon-rich stars. So here you have mass loss rate versus outflow velocity, and then the color shows you the refractory organic coverage. As you increase your density, you have more refractory organic material sticking onto the dust, so about up to 22% of the dust is covered, but on average it's quite low, 3 to 9%. So some of the dust can enter the ISM a bit sticky, and in fact you can increase this coverage if you tweak around with the physical parameters of your outflow. So the coating of the dust really depends on the outflow's properties. So it will be interesting to look with JWST, for example, to see how the surface coating changes throughout the outflow. If that's possible, I'm not really an observer, but it would be cool to do. So the effects of the physical structure of your outflow also have an impact on the dust that's being ejected into the ISM. All right, so when you look at this landscape of chemical models, in order to have a chemical model that covers the entire outflow, dust formation really is the missing puzzle piece to connect all these three types of chemical models, and only then will be able to follow a parcel of gas as it moves throughout the AGB outflow. All right, let's move on to the second part, which is chemical complexities within the gas phase. Because even though we understand the gas phase a bit better, it's still not fully understood. So in the inner wind, you've got a few weird molecules floating around. Because of the high density and temperature, you can assume that thermochemical equilibrium is a good assumption close to the surface. So carbon, if you have a C/O ratio larger than 1, all of your oxygen is locked up into carbon monoxide, for example. But in these carbon-rich outflows, water has been observed very close to the star, where it shouldn't be in equilibrium. And similarly for oxygen-rich outflows, HCN and CS, so carbon-bearing species, have also been observed close by. So that's a bit weird, they shouldn't be there, but that's all, precisely why you have these inner wind chemical models that include the effects of the shocks caused by stellar pulsations. Because the shocks could break up CO, liberate carbon, liberate oxygen, that then goes on to form all these funky molecules. And these models are reasonably good at reproducing most of the observations, but there's still some issues, for example, for ammonia or here for SO2, for example. Now, these semi-analytical models don't include any photochemistry because you can assume that your inner wind is nicely shielded by everything that's above it, in front of it. But if your outflow isn't spherically symmetric, you might have the case that some photons sneak their way in between your clumps. If your outflow is nicely spherically symmetric, you might have the case, it might be that some interstellar UV photons reach a region where that would otherwise have been well shielded. And I included this in a chemical model by using a porosity formalism. The porosity formalism divides your outflow into a stochastic mixture of clumps and an overdense clumps and a rarefied interclump medium. So you can have a two-component case, so your photons wiggle their way in between the clumps, and you can make it even more extreme where everything is inside of clumps, and in that case you will have even more UV radiation in your inner wind. And one way of looking at this porosity formalism, because it's still a one-dimensional model, is like it's a one-dimensional approximation of a three-dimensional outflow. It's like using APEX or a single-dish telescope rather than ALMA, like squinting a little bit. And we found that it has some impact on envelope sizes. It helps a bit with some molecules, but it's certainly not the answer for everything. However, if your funky, clumpy structure is caused by a companion, and if that companion is a star, you will have an internal source of UV photons in your dense inner wind. So that's something that I did with Tom Miller a while ago. We included the effects of an inner wind companion. And if your outflow is then a bit clumpy, your interstellar UV photons can reach further in, and your internal companion photons can reach further out. And then you create a very strange type of chemistry. And we found that the results all depend on the balance between two body reactions and photoreactions. So if your two body reactions are faster than photoreactions, so if things can bump into other things and go on, can create a new molecule, before they are photodissociated, you find that the complexity of your outflow increases and some of your daughters start to behave like parents. If you're, on the other hand, your photoreactions are faster than your two body reactions, things as in molecules and atoms don't get a chance to go on and react. They are photodissociated before any other chemistry can happen, and your outflow will appear to be molecule poor. And this balance all depends on the density of your outflow and the clumpiness. Just how dense things are dictates how easily things can bump into each other and react. And a nice application of this model was a study led by Thaisa over here, where she found that SIN shows this anisotropic emission around W Aquila. And W Aquila is a known binary AGB star, so we've got the AGB star over here, and at the moment the stellar companion is somewhere over there. And SIN is one of these molecules that you wouldn't expect to be present so close to an AGB star, but if you include a stellar companion, you can form quite a bit of it. And together, the wedge shape, together with some hydrodynamical modeling, allowed, well, mostly Thaisa, to then deduce the binary orbit, which is highly eccentric of this AGB binary system. So it's like a new astrochemistry-based method to constrain orbital parameters. So astrochemistry, observations, hydrodynamical modeling, all collaborating to constrain the dynamics of a system. Now, again, this is all still a one-dimensional model, and you can poke some holes and make it a bit more clumpy, but if you have specific structures, you will need specific models. And for example, certain binary interactions are thought to create circumbinary disks, and then you might wonder, well, I might wonder, whether these AGB disks have specific chemical signatures, and are they maybe similar to protoplanetary disks or not? And a perfect disk to start with is L2 Puppis, which I already shown before. It's perfect to start with because it's very well observed. It's the second closest AGB star at 64 parsec. And here you have this nice edge-on dusty disk. And if you combine that with ALMA data, there is a blob, and the blob might be a planet. The planet might form the disk. We don't know exactly how the disk is being formed, but we do know it's there. So let's continue with that. That's what I did at Leeds, together with Catherine Walsh, because she's an expert in the chemical modeling of protoplanetary disks. So let's look at an AGB disk. And first, we retrieved an updated physical structure of the disk. So I modeled these previous ALMA data. So you've got the moment zero map of 12 and 13 CO and J3 to 2 lines. And I used a parametrization commonly used for protoplanetary disks to see if we could retrieve a physical structure, and we could. So this is what we found. It is quite a small disk, so 15 AU radially, about 10 AU vertically, but which is, well, maybe a bit small for a PPD, but it's definitely very warm. So about like 900 Kelvin within the midplane. This is much, much warmer than you would expect for a protoplanetary disk, but not for an AGB disk because there's like a star right there, well, a red, very red warm star, and it's made out of, well, outflow material. Anyway, we plugged this physical structure into the protoplanetary disk chemical model, and we had some interesting results. So here I show you the output of CO over time. So it's after 1,000 years, 10,000, 100, 500, and then finally a million years. And CO still looks like you would hope it looked. So everything, model seems to work. You still have CO in a disky shape, and it corresponds well to the observations. SO is another parent species because L2 Puppis is oxygen rich. So over time you see that it decreases a bit in abundance, but after 500,000 years this gap starts to appear in the midplane, and SO has previously been observed, and we don't see this gap in the observations. The resolution would have been high enough to observe the gap if it would have been there. So, assuming our model is right, big assumption, we can tentatively age the disk of L2 Puppis. It can't be too much older than 100,000 years, because otherwise you have a gap in your SO. And another nice result is that we have quite a lot of carbon-rich chemistry, which is surprising since it's an oxygen-rich outflow. We start off with lots of oxygen-rich material, and then the products, your daughters, are surprisingly carbon-rich, including these complex organic molecules that are being formed in the midplane, and quite abundantly so, especially if you compare the column densities with the column densities for a AGB outflow model. So they're much, much more abundant than in oxygen-rich outflow. So turns out that the chemistry, well, that your disk really impacts the chemistry within it. And you could use chemistry as a way to observe or sort of identify disks that aren't as easily observable as the one around L2 Puppis. And if you want to know more about its rich chemistry, then you can go and read our recently accepted paper on it. It's quite fun. All right. But a disk is still a very specific structure. If you want to go to more general structures, you need to go to hydrodynamical models. And so far, we've got some quite promising results. For example, this hydrodynamical model looks a lot like that star, but that was purely by coincidence. The model wasn't produced to reproduce our hydra. And also, you can't directly compare a hydro model to your observations, because hydro gives you output in density. You then need chemistry to convert that to an abundance, and radiative transfer to convert that to an emission profile. So here you have an example of that for the phantom model of phantom hydro model of W. Aquila, the funky wedge shape of Thaisa, and then finally the MC Fost CO radiative transfer model. So you still see some shells, you still have the wake, but it's not quite as clear. Well, the signatures aren't quite as clear. You can do this for CO because it's quite simple chemically speaking, but if you want to do it for other species, you will have to include a chemical network, and maybe even a complete chemical network, and that will become very computationally expensive to include in your hydro model. But you can make a chemical emulator, sort of faking, well, not faking, pretending that you have a chemical model using machine learning. It's all very fancy, and Silke Maas did it. She's a PhD student at KU Leuven that I co-supervised. So she made the first chemical emulator for an AGB outflow. The dashed lines that you can sort of see here is the output by the one-dimensional model, and then the solid lines is what her chemical emulator puts out. So it looks a bit like you just drawn these abundance profiles by hand, which is really, really nice. And this speeds up the process of including your chemistry quite a bit. Like now it's just a factor of 20, but it could be much faster as well. And if you want to know more about that, she's giving a talk at ACES next week. So I will leave the details to her. All right, I still have quite some time. I went a bit faster than expected, so that's good for everybody, I think, because it's already 12:30. But I'd like to talk a bit about what I'm doing now, which is to really dive into the chemical model itself by doing a sensitivity analysis. So if you have this reaction, the rate with which the abundance of your product C changes is given by this equation. So you've got the abundances of your reactants A and B, and then a proportionality constant, which is called your rate coefficient. And at the heart of every chemical model lies the chemical reaction network. So this is a collection of all the reactions that you include in your model, along with their reaction coefficients, with the rate coefficients. And the reaction network that I use is the latest release of the UNIS database for astrochemistry, and there's 8,767 reactions among 737 species, and each of these reactions has a reaction rates as an associated uncertainty, and most of them are quite well constrained, so less than 25%, less than 50% error, but other ones have a factor 2, a factor 10, and then a few are highly uncertain. And if you calculate a chemical model, you don't take these uncertainties into account, you just plug it in and you believe what it says. So what I've been doing is to do the first sensitivity analysis for such an AGB model. So I do some Monte Carlo sampling. I assume that my error is log normally distributed for the reaction rates, and then the width of my error is well, proportional to the uncertainty. And then I just draw 10,000 samples, so 10,000 models. I do this for carbon-rich, oxygen-rich, different types of different mass loss rates as well, so 60,000 models in total. And this is an example. So if you have C2H2 in carbon-rich outflow, I mean. So this is the result that you get from your standard abundance rates, and then you vary the chemistry. You sort of shake it around, is how I visualize it. And this is then what you get. So you can divide it into a 1 sigma, 2 and 3 sigma curves. And then the 2 sigma curve, so this contains 95.4% of all of your model output, can be seen as the error. So this is another example of your output. So rather than having a nicely defined predicted abundance profile, which is just very narrow, you now also have the error on your abundance profile. So the envelopes of your molecules are a bit fuzzy, which can be quite important, especially for CO, as you use CO envelope sizes to retrieve mass loss rates, for example. And then if you look at daughter species, you've got an error here on their peak abundance. Some are quite small, some are quite large. It all depends a little bit on everything that happens before it. So what I'm doing now is to do first an uncertainty analysis to see what the uncertainties are on the predicted abundance profiles, and maybe it has any implications for data retrieval. And then the sensitivity bit is to determine the key reactions. So which reactions have the largest impact on your uncertainty? And this is mainly to guide laboratory experiments, because it takes one postdoc, 1 year, to measure one reaction rate. And yeah, it's a bit sad if it then doesn't impact the chemistry. But yeah, so that will be useful to guide lab experiments. And then while I was doing all of this, I ran into some existential crisis, and I had to turn to philosophy of science to really determine what it all means. And I collaborate with Marie Guéguin, who is in Rennes in France. So if you have any questions or are interested in like funky statistics and or philosophy of science, let me know. That would be cool. And then I'll end with my conclusions. So I hope I convinced you that chemistry plays an important role in AGB outflows. It's linked to the dynamics, since it's a process of dust formation that launches your outflow. It determines the composition of your outflow and the dust, which is very important to the chemical enrichment of the ISM. And developing chemical models and doing a sensitivity analysis is essential to unravel the process of dust formation and interpret complex observations. So thank you for your attention.
About also regarding the dust formation, it's also an issue with characteristic and interstellar planet formation. So are there some similarities between these things, and how you process that?
Yeah, so in the protoplanetary disk, you already start out with quite a bit of dust that's there, and then the issue is more of how do you get them to become planets, whereas we start out with molecules and we have to form dust, so it's more of the embryonic phase of dust formation rather than, the more advanced stage of planet formation. So we really have to go from gas phase to solid state and go through this phase transition. But it's also like dust is also being formed in the ISM, and that's also not quite certain. So the AGB stars and supernovae, they produce a lot of dust, but it also gets destroyed in the ISM, and then gets reaccreted via mysterious ways as well. But it's maybe more similar to the ISM dust formation, although very, very different densities, of course. So I think it's more a very specific problem to an AGB outflow, how you go from molecules to dust grains at these higher temperatures and densities. So it's quite a unique problem.
If I understand correctly, the main difference is that planet formation, you already have some seeding dust, some supernovae, whatever.
Yeah.
You should see, well, here the origin of the molecules is from the CO.
Yeah. You start off with molecules, and exactly. You have to go from molecules to dust grains rather than from dust grains to planets. Right.
Nice talk. You mentioned the carbon-bearing molecules found around oxygen-rich stars. So could that, talking about dust formation, could that lead to carbonaceous dust forming around oxygen-rich?
That would be interesting to take a look at. Something that I would like to do by including dust formation routes as well. because if you have a companion, for example, you also have a lot of they also produce these carbon-bearing species around oxygen-rich outflows, but then how efficiently they get sequestered into the dust, that's not known, but that's something that would be very fun to look into, and especially also like the dust around L2 puppies, like within the disk, maybe it's also a slightly different composition than you would expect if there's like carbon grains sticking onto it. But yeah, that's something that I'd like to look into in the future.
Because there are some silicon carbide grains that just, you know, they have a nitrogen and C12, C13 that kind of suggests they haven't really undergone.
All right, yeah.
They're a bit strange, so.
I know that is something that I'm planning on doing in the future, to include dust nucleation like a dust nucleation network in the model, in collaboration with like chemists, of course, to get all these reactions, and that will be interesting to see if you can, like, what the effect of a companion would be. Yeah, because yeah, that would be nice. Yeah, if I could get a reference, that would be, yeah.
So I might miss your conclusion about the UV shining from inside into the porous output. So is that more important than the UV from outside?
Well, it all depends, but it can be more, well, chemically speaking, it can be more important, because if you have a very strong UV field, then it looks like, well, your outflow will appear to be molecule poor. There's just CO and some other molecules floating around. Everything else will be atom or an ion. But yeah, depending on the companion and the porosity of your outflow, it can actually have a very large impact and make your outflow look quite odd compared to UV, well, interstellar UV only. So yeah, it could be more important. Depending on your outflow, it can be more important, yeah.
So UV isn't strong enough to, I guess, destroy your testing?
No. Dust is quite photostable, so that's also the only thing that survives into the ISM. All the molecules get destroyed, but dust is very stable, so you can just blast UV photons at it. It will maybe, like, some pieces will break off, but the dust will still be there. But it might have an effect on the composition of your dust, because your parents, well, your molecules from which you form the dust will be different. But yeah, so dust and PAHs survive. That's it. Everything else was for nothing.
Does anybody else ask a question? Yeah. I have a question about like the first slides. Having this nice plot of different from densities and temperature, time scales.
Yes.
The first 5 minutes. I just wanna.
There you go. This one.
Yes. Good. Thanks. Yeah, I just wanna understand like the intuition, because you're saying that initially you have this non-equilibrium chemistry, right? I think usually when we have something which is not equilibrium, usually, physics will compare time scales. So at least here, we have typical time scale for stellar evolution, maybe also have time scale for the mass loss. But how do you estimate time scale for, chemical dynamic process?
So the chemical equilibrium is more of a density and temperature consideration. So if density and temperature is high enough and you just leave things, you just put a bunch of molecules on a pile and you look away, things will, well, you want to minimize the Gibbs free energy, so you don't actually need to look at a time scale, it's just you will minimize the Gibbs free energy. But when it's non-equilibrium, you can also look at time scales, and then it all depends on the reaction rates of your chemical reactions that are going on. So I'm not an expert in the equilibrium chemistry or the non-equilibrium bit in the inner winds, but the equilibrium chemistry is more of a thermodynamical exercise. You minimize Gibbs free energies and you get a certain composition out of it. Whereas as soon as you have chemistry that's happening, you need to go to your chemical reaction rates, and then you have time scale as well. Some reactions are much faster than other ones, for example. Yeah. Yeah. Yeah, exactly, and the density as well. Well, yeah, because density, exactly. Yeah, thanks.
Well, this is up. Does this change much depending on whether you're looking at the AGB or pulsing, or is this quite separate to interstellar evolution?
So I think as soon as you have your outflow, but like maybe Amanda and Thijs can correct me on that, you will have like these 3 regions. What happens as you move through the AGB, if you undergo enough dredge ups, the C overall ratio will change and you will go from oxygen rich to S-type to carbon rich if you're massive enough, of course, and not too massive. So like a little sweet spot. But if you have like a thermal pulse that's going on, of course you will sort of mess up whatever's going on in the inner wind, and that will propagate throughout the rest of the outflow. But you can sort of say that all of the messiness, I think, is more confined to the inner winds, and things have sort of chilled out a bit over here, and yeah, you can form your dust. I think, if that's correct, right here. But yeah, once you have an outflow, it's just a gradient. Right, yeah. You might have to shake things around in the beginning, but that's it. So could you expand on the link to philosophy of science you mentioned? Also, can you reverse engineer the chemistry or modeling to infer the original atomic composition at the surface of the star? So let's start with the second question. I suppose you could, but then you need observations of every molecule, and some of the molecules are have a very low abundance, so that means that you wouldn't really be able to observe them. So maybe like a bunch of silicon or sulfur is stuck in something you can't observe. So I don't know, it would be quite hard. And the link to philosophy of science. So I started sensitivity analysis as a fun lockdown project. And I was doing I calculated all the models, because of course you can just calculate a bunch of models, that's fine. But then I was looking at it and thinking, but what does it all mean? And one of my friends, so at KU Leuven, if you do philosophy, you can choose a minor in whatever you want. Well, you would, well, back in the day at least. And there were some philosophers doing physics, so I befriended a philosopher. And then she went on to do a PhD in philosophy of science. So I thought, like, wait a minute, that's her job. So we Zoomed over the pandemic. And turns out that her friend, Marie, had just started a Marie Curie fellowship. So I was also a Marie Curie fellow. So our emails were really, really like, hey, Marie Curie. So she started a Marie Curie fellowship at Rennes, specifically looking at the philosophy of sensitivity analyses in astrochemistry. So I was like, whoa, okay, that's amazing. Very coincidental, but wonderful, because it turns out that all the sensitivity analyses that are being done in astrochemistry are not what other fields do. So everybody else does it in a very specific way, and they all agree on how you should do it, and we just like do something completely, not completely different, but we don't agree with each other, or people don't like that the model has an uncertainty associated with it as well. So like the community is a bit hesitant apparently, and then we just do whatever we want apparently also. So it's quite useful to have her guide me through the literature, because why reinvent the wheel if somebody already made beautiful wheels right there? So yeah, that's the link with philosophy of science. A nice coincidence, and now very confusing.